Hello. In this video, I'm just going to go through some selected problems from the homework in Chapter 5. Um, so I'm hoping this is sort of the best way to reach you, the best way for you to understand maybe if you made a mistake on one of these, or you can check to see if you're right or if you did it a different way. Um, anyway, I'm just hoping this helps you in some way to see some solutions for a few problems from Chapter 5. I know that relations can be pretty tricky. I remember when I first learned these, yeah, there's definitely a learning curve to these, and it's definitely helpful to see some worked out in real time like this. All right, so let's get started. So first, I'm looking at this one, 5.1, number 7. Remember, in this one, our set S is these numbers 1, 2, 3, and 4, and I'm just going to work out part A and part D for this one. I'll save B and C for you to think about once you've seen these. And we want to test reflexivity, symmetry, and transitivity for each one of these. We want to be able to tell what properties they possess. All right, so for R1, remember reflexivity. So let's ask the question, is this thing reflexive? So that is A related to A for all A in S? So is 1 related to 1? Nope, I don't see the pair 1, 1 here, and so immediately this fails. In fact, no A is related to A. Some might say it's anti-reflexive. All right, symmetry. So remember in this one, I'm asking, so if I find that A is related to B, then I also have to have B is related to A. So for example, here I have 1 is related to 2. And so if I'm testing for symmetry, I need to check, is 2 also related to 1? And it is. And so that's good. And that goes the other way too, right? 2 is related to 1, and 1 is related to 2. And so those two pairs check out. All right, 3 is related to 4. Is 4 related to 3? Yes. And then the other way around as well. 4 is related to 3, and 3 is related to 4. And so this checks out, yes. It is symmetric. What about transitivity? So in this one, I'm going to we need to look for triples, A, B, and C, with A related to B and B related to C. And then once I locate a triple like that, I can check to see, is A related to C in that case? So for example, all right, 1 related to 2, and 2 is related to 1. So see how they share that middle term. Those are the kind of pairs of pairs that I want to check. And what I'd be looking for is, are the outsides related to each other? So in this case, I have 1 related to 2 and 2 related to 1. If it were transitive, I should see 1 is related to 1. However, I don't. 1 is not related to 1. And so this fails transitivity. So transitivity, those are the only pairs of pairs that I should check, is if they share a common middle term, and then I'm checking the outside. So we'll see another example of that in part D. So we've already finished off part A. It was symmetric, but not reflexive and not transitive. All right, so for part D, R4 is this one. There's just 2 pairs in this relation. And so let's ask ourselves, so reflexive. All right, reflexive is pretty easy to see. I just want to check every item in my set, 1, 2, 3, 4, and see if it's related to, see if each one is related to itself. Here I don't see anything related to itself, and so this is, no, it's not reflexive. Symmetric. Symmetry, should be a question mark. Is this symmetric? So again, I'm checking, okay, here I have 1 related to 2. So if this were symmetric, I should also see that 2 is related to 1. But that doesn't appear anywhere, and so this fails symmetry. All right, what about transitivity? Remember, this means if A is related to B and B is related to C, then A is related to C. So I need to check all occurrences of these 2 things happening. So if I can find 2 pairs, such that A is related to B and B is related to C, then I need to check that A is related to C. Okay, so let's see if we can find such a triple. All right, 1 is related to 2. Do I see 2 related to anything else? Nope. Okay, so there's no overlap of 2 in the middle anywhere. So there's nothing to check for that pair. And then 3 related to 4. Do I see 4 related to anything? No. So this is a kind of a weird one, but no A, B, and C satisfy the hypothesis. Okay, so what does that mean if my hypothesis is always false? So this is an implication, right? Transitivity is an implication. It's a universal statement over this implication. For all triples A, B, and C, this has to happen, but there are no triples for which the hypothesis is satisfied. Therefore, this implication, remember, if the hypothesis is false, the implication's true. And since this is false for every triple A, B, and C, this implication is always true. And so this one actually is transitive, yes. And in this case, when we have this, when the hypothesis of an implication is always false, when we're thinking of transitivity or symmetry, anytime we have some implication, we say that it's vacuously true that this is transitive. So yes, and we say vacuously. So it is vacuously true that this is transitive. So that's a bit of a weird one, hence why I wanted to go over it. All right, let's make our way to 5.1, number 10. So now we're getting into defining relations using an open sentence rather than just listing the pairs. So here, again, I'll just do A and D for this one. We know our set, this is important for reflexivity in particular, our set R. And then our first relation, R1, is X is related to Y if the difference between X and Y is less than 1. So you may not yet be thinking about absolute values like this, but I'm going to try and push you to think about absolute values like a distance between X and Y. That's sort of the intuition you need to solve this one, is that absolute value of X minus Y, well, that's the distance between X and Y. It's always positive, and it just tells me how many, what's the length of the interval between X and Y. So if X and Y are related, that means the distance between them must be less than 1. Well, it should also follow, certainly, that every real number is related to itself. So let's check that. So is this thing reflexive? Oops, I've been using blue for my solutions. Is this thing reflexive? So we ask ourselves, is let A be in R, then let's compute A minus A and see if that's less than 1. So remember, reflexivity is A related to A for all A in R. And so if I want to know in this case, I want to plug in A for both X and Y. So some people like to do this, right? For reflexivity, let X equal A equal Y. Let them be the same thing. Let them both be called A. Well, A minus A, the distance between A and itself is 0. And that's certainly less than 1. And since this was general, right, this was an arbitrary real number A, we can say, so A is related to A for all A in R. Cool. What about symmetry? I did post about this one on the discussion board, but maybe you didn't see it. So is this thing symmetric? So assume X is related to Y. Remember, symmetry is if A relates to B, then B relates to A. So we're going to check these cases. We're going to look at all pairs where A is related to B and check and see if B is related to A. So if A is related to B, or let me change that to A and B. Why not? So assume A is related to B for these two real numbers A and B. What does that tell us? Well, that tells us that A minus B is less than 1. Okay, so is B minus A then less than 1? Well, yeah. Notice that B minus A is the same thing as negative of A minus B. And so if I go ahead and put absolute values around everything here, these should be equal. So absolute value of B minus A is the same thing as absolute value of negative A minus B. But if I stick a negative inside of an absolute value, it's not gonna do anything. If I have a factor of -1 inside of there, I can get rid of that under the absolute value because I know the absolute value will just make it positive. And so this is just absolute value of a minus b. And we know by assumption that absolute value of a minus b is less than 1 because a is related to b. And so what this tells me here is that b minus a, absolute value of b minus a is also less than 1. Hence, b is related to a. And so yes, it is symmetric. So reflexive, yes. Symmetric, yes. What about transitivity? Okay, well, think about it first. Maybe try some things. Sort of armed with this intuition that the absolute value of x minus y is the distance between them. So this relation is really saying two things are related if their distance, if the distance between them is less than 1. Well, okay, so with transitive, this is saying, okay, if two things, the distance between x and y is less than 1, and the distance between y and z is less than 1, then is the distance between x and z less than 1 all the time? Well, that seems a bit ridiculous, right? So just off the back with that intuition, I can maybe construct a counterexample to prove that it's not transitive. So what if I let x equal 0? Let's say y equal, I don't know, 0.9. I don't want to, strictly less than 1, so I didn't want to choose 1 for y. And let's keep going farther out, but still within 1 of 0.9. So how about 1.8? Then, okay, so distance between 0 and 0.9 is 0.9, which is less than 1. So 0 is related to 0.9. And the distance between 0.9 and 1.8, that's also 0.9. So 0.9 is related to 1.8. So I have 0 is related to 0.9, 0.9 is related to 1.8. So if this were transitive, I should get 0 is related to 1.8. However, let's compute their distance, 0 minus 1.8. Well, that's a distance of 1.8, which is not less than 1. And so 0 is not related to 1.8. Hence, it's not transitive. So in order to build this intuition, right, that's what really helped was transitivity, to be able to identify, hey, we need a counterexample here rather than I should try and prove it. In the next one, I'll show you another kind of technique. We'll try and prove it first and see that, oh, something's not quite right here, and that'll lead us to a counterexample. With this one, I had this intuition of distance between two numbers, and I realized the distance is really not transitive, that the distance can keep growing even though the distance between pairs are small. Okay, so that's the idea. Let's take a look at part D. X squared plus y squared equals 9 is my relation here. Again, we're on all real numbers. So is this reflexive? So we might try and just plug a into this. So let's see, is a squared, so let a be a real number, a squared plus a squared equals 9. And what do I get? I get 2a squared equals 9. I can keep trying to solve this. I get a equals square root of 9 over 2. Okay. So wait, so I assumed that a was related to a here. That was my initial assumption here, that a is related to a, and I just wanted to see what would have to be true in order for a to be related to a. What consequences of that are there? And I saw that a would have to equal square root of 9/2. Well, that's not going to work for all a. A could be any real number, right? So this one is, right, this is sort of absurd to think that a should be related to a for all a. So in particular, let a equals 0, then a squared plus a squared equals 0, which is not equal to 9. So a is not, or I'll say, I just need to find 1 value, right? That's why I can let a be 0. So 0 is not related to 0. And so this is not reflexive. There's at least one real number that isn't related to itself, and so it's not reflexive. All right, what about symmetry? So we'll assume a is related to b for two real numbers a and b. What does this mean? Well, this means that a squared plus b squared had better equal 9. And I'd like to show that b is related to a. So I'd like to show that b squared plus a squared equals 9. Well, that, again, that seems obvious because addition is commutative. So b squared plus a squared is the same thing as a squared plus b squared, which we know by assumption is 9. So we have b squared plus a squared equals 9. Hence, b is related to a. So if a is related to b, then also b is related to a. So this one is definitely symmetric. All right, what about transitivity? So for this one, this might be a little bit hard to see. So we're going to make our assumption. So assume a is related to b and b is related to c. So what does this tell us? This tells us that a squared plus b squared equals 9. And let's see, what else does this tell us? This tells us that b squared plus c squared equals 9. Okay, and I'd like to conclude that a squared plus c squared equals 9. So one sort of common thing you can do for transitivity, because you'll end up with two of these types of equations by assumption, and usually once you get down to an equation like this, maybe you can subtract them, because I'd like to get something about a squared plus c squared. Right, so I could try subtracting these. But what happens if I do that? So a squared plus b squared equals 9. I'll subtract the two. I'll get a squared minus c squared equals 0 after subtracting those two equations. And what this would tell me is that a squared equals c squared. So if we have a related to b and b related to c, then it must follow that a squared is equal to c squared. Notice this isn't telling me that a is related to c, just that those two things have to be equal. But if, right, so a squared plus, I'd like to see, is a squared plus c squared equal to 9? That's my question, because that would mean they're related to each other. Is a squared plus c squared equal to 9? Well, I know that a squared is also equal to c squared, right? By what I showed above. So that would imply a squared is c squared. So this is what I could write. This is 2a squared. So is 2a squared always equal to 9? Well, no. So if we have a related to b related to c, then this happens, and then hence this is the state of a squared plus c squared. And that's not always going to be equal to 9, right? This is, again, only going to happen when a is what? Square root of 9 halves. And that's not always the case. So let's try and construct a counterexample. It seems like this isn't going to be transitive, and so we should try and find a counterexample. Okay, so what are just example of two things that are related? I know if I let a be, say, 3 and b be 0, that's an easy way to find two things that are related. So I'll say here, let a equal 0 and b equal 3. Okay, so since 0 is related to 3, I would also know that 3 is related to 0. Yeah, why don't we go with that? Let it be equal 3 and c equals 0. Right, so I know 0 is related to 3, since 0 squared plus 3 squared equals 9. And I know that 3 is related to 0, well, by symmetry, or I could just check the equation. But is 0 related to 0? No. is 0. 0 is not related to 0. And so this fails transitivity. I found a triple, 0, 3, and 0, such that A is related to B, B is related to C, but A is not related to C. And so this fails transitivity. All right, let's keep moving through these. I feel like this video is going to be longer than I want, so maybe I'll post some timestamps or something for when I look at specific problems. Okay, yeah, let's take a look at moving on to 5.2, number 4. This one, yeah, some people had some questions about this. One of you posted a really nice sort of explanation for how you did this. So I guess I'll sort of just use that kind of line of thinking. So remember that these are equivalence classes, and that the set of equivalence classes is a partition. So that means no matter what equivalence relation I'm looking at, if I compare two equivalence classes and I look at their intersection, let's say, that this is either the empty set. In this case, that would tell me that A is not related to B. So remember, partitions are disjoint, or the sets in partitions are disjoint. It's a pairwise disjoint. So if I look at two sets in the partition, either their intersection is empty or they had to be the same set. And so either A, equivalence class containing A, and equivalence class containing B are disjoint, in which case A is not related to B, or, and this is for all A and B in my set, and no matter what the equivalence relation is, or I have that A intersect B is not empty. And what would that mean? If it's not empty, then these must be the same set. And so that is A is in the equivalence class containing B. And so this would tell me then that A is related to B. And of course we get symmetry, B is related to A, and so forth. Up here, this would tell me that that A is not related to B, that they're in different equivalence classes. So that's what this first bit is telling me. It's telling me, hey, this element U, it's in both the equivalence class containing X and the equivalence class containing Y. So this is a really loaded bit of information because it's telling me two things. One, it's saying that equivalence class containing X the equivalence class containing X and the equivalence class containing Y are not disjoint. And so that means where in this case, that means that equivalence class containing X is the same as the equivalence class containing Y, hence X and Y are related. And it's telling me the element that's in there. U is also in that. And so that's telling me equivalence class containing U is the same as the one containing X and the one containing Y. That is the U, X, and Y are all related to each other. So I'm going to draw a little diagram for this one as we sort of piece through this information. So here is my set S. And that first bit of information just told me that X, Y, and U must all be in the same equivalence class. So remember how I can sort of depict partitions? I'll have all my elements in S, and I'll just divvy it up. So here's I could call this equivalence class containing X, or equivalence class containing U, or equivalence class containing Y. That would all work. That's this part. All right, let's see what else we can see. Z is in the equivalence class containing V. So all that's telling me is that Z and V are related. And so that means they are in their own equivalence class. There might be more in it, so I'll leave some room in case. But they're definitely by themselves. And, well, actually, wait a second. Do we know that they can't be in here? In the equivalence class containing X? That's where part B comes in. I had to check myself there. Take a look at part B. It says V is not in the intersection equivalence class containing X and equivalence class containing Y. So that this bit right here, this is this equivalence class right here. They're the same thing, so when I intersect them, I get the whole set because they're exactly the same set. And so V is not in there. That's telling me V is not related to X, it's not related to Y, and it's not related to U. And so definitely it's over here in its own equivalence class, and part C is telling me that Z belongs with it. All right, nice save. So that's B and C tell us that. But again, still, there might be something else in there. So W is in equivalence class containing U, union equivalence class containing Z. Wait a second, that seems wrong. 5.2 number 4. Maybe I wrote this down wrong. Yes, I did. So that wouldn't that wouldn't really make sense. That would mean this thing is not a partition. This should be a not inside of. W is not an element of U. So it's saying W is it's not an element of equivalence class containing U, and it's not in the equivalence class containing Z. And so it must be by itself. Right, so this one, I saw some questions about this. So W not in that. This is the same thing as saying that not W is in U union Z. So that's, right, so this is equivalent to not W in U or W in Z, equivalence class containing U. And so now we can apply De Morgan if we're wondering, hey, what exactly does this mean to say that something is not in the union of two sets? Well, it means that W is not in U and W is not in equivalence class containing Z. So it's outside of both of those things. Here's the one containing U, here's the one containing Z. It must be outside of those two things. And so that means W must be over here by itself. And so that's how we can piece through a solution, that solution. So actually we should check and see, did we really answer the question? So the question asks, what is the relation? And so you might be tempted to give the pairs here. So I can start doing this. So X is related to Y. You know, Y is related to U. We can list all the things in that equivalence class. Y related to U, U related to X, and also we know that, you know, X has to be related to X. It's in its own equivalence class. Y related to Y, U is related to U, and also these backwards one. If Y is related to U, U is also related to Y. So we can list all of those, but actually the partition, if I give the partition, that contains all of the information for the relation, right? This is telling me X is related to Y, and U is related to X, and Y is related to X, and X is related to X, and Y. It's telling me all of those pairs by just giving you this partition. So it's actually acceptable for you to just tell me the partition. That's sort of another way to give me an equivalence relation, or to describe or define an equivalence relation, is through the partition. So I'm gonna call this one with this one good. All right, let's see. Do I have any more there? No. 5.2 number 10. Okay. Right. So this one was also tricky for some people. I had some questions in office hours about this one, so I thought this would be a good one to go through. One first tricky bit is that it's a relation on a Cartesian product. So this is a relation on pairs of integers. That's why it's defined like this. AB, that pair is related to CD if A plus B plus C plus D is even. All right, so this is one that definitely takes a bit to understand what each property means in this case. So let's start going through it. Reflexivity. So here I want to check that every pair of integers is related to itself. So let AB, there's an arbitrary element of this Cartesian product. So I don't just have A like in the other ones. I have an arbitrary element of my set. In this case, a Cartesian product. And so I have an arbitrary integer paired with an arbitrary integer like that. And now I want to check, is AB related to AB? So let's figure that out. If AB was related to AB, I would have A plus B plus A plus B being even. So let's compute that. A plus B plus A plus B is what? That's 2A plus 2B. Notice I can factor 2 out. That's 2A plus B. And then since A and B are both integers, A plus B is an integer. And that follows that a plus b plus a plus b is even in this case, right? It's twice an integer. So the pair AB is related to itself. We just proved that. So I think once you get over this hurdle of, right, an arbitrary element is really a pair here, this one's at least not too hard to see. So it is reflexive. Ding. Okay, what about symmetry? So here, right, we want to show if A is related to B, then B is related to A. So for symmetry, assume, oh, but A and B here, right, we're talking about pairs. So assume AB is related to another pair, CD. And I'd like to conclude that CD is related to AB. So what does this mean that AB is related to CD? That means A plus B plus C plus D is even. Okay. Is CD related to AB? Is C plus D plus A plus B even? Well, sure. Again, addition is commutative. So I'll say then C plus D plus A plus B is even because the two things are equal to each other. So CD must be related to AB. So yeah, it is symmetric. Is it transitive? Let's check transitivity. So now what'll my assumption be? That some pair is related to another pair. AB related to C. I caught myself there. I was going to put B, C, but that's not right. It should be related. It's related to this other pair CD, and CD is related to some third pair. I don't know, EF. So we'll assume those two things. So what does AB related to CD tell me? That tells me A plus B plus C plus D is even. And this one's telling me that C plus D plus E plus F is even. Okay. So again, we're in the situation where we have these two open sentences over these. And what I could do is transfer these to equations. So write this in some kind of equation. The fact that it's even, right, we know it means it's equal to 2k. And then in order to get, right, so what do I want to conclude here? I want to show that, or prove that that there's some example that doesn't, that AB is related to EF. So that would be A plus B plus E plus F is even. So how can I get a hold of this sum, A plus B plus E plus F? Well, if I take this equation and I subtract this one, I won't have quite that sum. It'll be subtracting E and F, but maybe there's something I can work with there. So I'm going to try that and just see what I end up with. So A plus B plus C plus D equals 2k. Since it's even, it's equal to 2k for some k in the integers, and over here I can say it's equal to how about 2L for some L in the integers? That's what being even means. And then I'm going to take those and I'm going to subtract them. So I'm going to get A plus B minus E minus F equal to 2K minus 2L. Now here I don't quite have what I want. I want plus E plus F. Well, how can I change a minus E to a positive E? What can I add to this to get to a positive E? Well, I could add 2E to this. So this is the strategy here. I'm going to add 2E and I'm going to add 2F. And maybe you can see then, since I'm adding a multiple of 2 to these, it's going to preserve its parity. It's going to preserve the fact that it's even. And so let's do that. So I'm going to add 2E and 2F to both sides. So I better do the same thing over here too. Plus 2E plus 2F. And what do I get then? I'm going to get A plus B plus E plus F equal to 2k minus 2l plus 2e plus 2f. But again, everything has a 2 in it, so I can factor that out. This is k minus l plus e plus f. So it's twice this. This is an integer. And so it follows that a plus b plus e plus f is even. Okay, so that one was kind of a tricky one, but we got to it. We showed that this is even, and hence this is transitive. So we do have an equivalence relation here. Okay, but we're not done with this problem, are we? There's a part B to this, which asks to describe the equivalence classes, right? Since we have an equivalence relation, we should be able to describe what the equivalence classes look like. All right, so I'm going to tell you, I haven't looked at this problem in about, 10 months, something like that. So I've kind of forgotten exactly what the equivalence classes look like. And I didn't go through this and figure them out before recording this video because I want you to see the process that I'm going to go through to try and figure out what the equivalence classes look like. So you might try just picking some values first. So I don't know, let's let A equal 1 and B equal 2, something like that. We'll just pick two integers and see what is the pair 1, 2 related to. Well, I know that it's related to C and D if A plus B plus C plus D is even. So A plus B by itself is 3. And so if I want A plus B plus C plus D to be even, I need 3 plus C plus D to be even. So if C plus D itself is even, then I'll have an even plus an odd, which will be odd. So I really need C plus D to be even. Or sorry, I need C, wow, what did I just say? Right, so 3, right, if C plus D is even, then it's no good. The total sum will be odd. So I need C plus D to be odd. So I need the sum of these two things to be odd. That means I must have an even and an odd, because an odd plus an odd is even, and an even plus an even is even. So here I started with an odd and an even. That turned out to be odd, as we know. And I would need C and D to be different parity. I would need C to be even and D to be odd, or the other way around. So it seems like, right, so I'm hot on the trail of what these equivalence classes look like. So if A and B are opposite parity, and AB related to CD, then I know that C and D also have to have opposite parity, because I'll need to get an odd out. Opposite A and B being opposite parity means I'll end up with an odd for their sum, and then I need another odd, so C and D have to be opposite parity. Then C and D are opposite parity. And that's very general, right? And the other way around will work too. If C and D are opposite parity, then A and B have to be opposite parity. And so it seems like one equivalence class would be, well, all right, let's think about that. So if AB is opposite parity, it's related to anything else that has opposite parity. So it seems like, okay, so starting to build the equivalence classes here. So this would be AB, where A and B are opposite parity. So they're related to themselves, and any two pairs of integers that are opposite parity, that are each opposite parity, will result in an even sum. And so that's one big equivalence class, is AB opposite parity. So it seems natural that my other equivalence class should be same parity. And we can check that, right? So if A and B are the same parity, then their sum would be even. And then if I want the sum of A plus B plus C plus D to be even, I would need C plus D to be even then, which implies they're the same parity. So over here, we have all A and B such that A and B are the same parity. So that's it. Those are the only two options, opposite parity and same parity, and they split up this Cartesian product, integers cross integers, into these two sets. So the ones of same parity and the ones of opposite parity. So that's one way to generate all the pairs of opposite parity and all the pairs with same parity is by this relation, or rather a plus b plus this relation here. That generates things of same parity and opposite parity. So that's one way to go about this is you just pick a value and see where that takes you, but try and keep it general. What was special about A and B? Oh, they were opposite parity, and what would that imply for C and D, and so on. So you kind of just pick something and then follow your nose, see what's going on. Maybe it takes a few more tries than it took me of picking things. Okay, let's move on to functions now. 5.3, number 6. So we have this function that goes from A to B. So if A1 and A2 are in A, so in the domain, then the image of the set A1 intersect A2 is inside of the intersection of the image of A1 and the image of A2. That's what I'd like to show. So this is similar to the previous one, number 5, where maybe you looked up the answer in the back of the book and had some idea how to do that. So this one's going to be similar, but notice here we have a set inequality, right? It's just subset. In fact, it's not true that these things are always equal like it is for union. Right, number 5, we're asked to show the same thing but with an equal sign here, and it's a union rather than intersection. And so when we do intersection, actually this is the only thing we can say. It's not always the case that the other subset works. Okay, so, all right, let's prove it. Assume A1 and A2 are subsets of A. They're in the domain. And then what I want to do is I want to show that this thing is a subset of that thing. So in order to show subsets, I give myself an arbitrary element here, x in here, and I want to show that x is in here. So that would mean x is in this image and x is in this image. So I want to show two things with this assumption that x is in the image of A1 intersect A2. And actually, I'm going to change this from x to y. It doesn't really matter, but typically we use y for things in the codomain because, I don't know, maybe you're more familiar with that sort of notation. So if y is in here, then y is in here, and y is in here. Okay, so we're assuming these two sets are in A, and now assume y is in f of A1 intersect A2. Okay, so if y is in the image of this set, what does image mean? Remember, f of A1 intersect A2, this is the set of all images of elements in A1 intersect A2. So if y is in here, that means y is an image of some element that's in A1 intersect A2. So that means then there exists x in this intersection, A1 intersect A2, such that f of x is equal to y. So it's the image of one of those things. And I'd like to conclude that y is also f of x where x is in A1 and where x is in A2. But look, I get that. X is in A1 intersect A2. That what follows from this, since x is in A1 intersect A2, x is in A1 and x is in A2. So using the definition of intersection. So since x is in A1, well, y equals f of x then is an element of f of A1, because y then is an image of something that's in A1. And on the other side, x is in A2, well, that means y is the image of x, and x is in A2, so y must be in the image of A2. And so we get these two statements. We get that y is in f of A1 and y is in f of A2. And so together, hence, so now using the definition of intersection again, y must be in the intersection of those two sets. F of A1 intersect f of A2. And that's what we wanted to show. Notice in part 5, if you're kind of trying to follow the proof in the book and apply it to this one, remember in 5, this is an equality here, and so they'll show another direction to this. They'll take an arbitrary element of this set, and show that it goes in this set. We don't have to do that here because we just have the one direction. We just want to show subset. And we've done that. Okay, last one. This one comes from 5.5. So 5.4, I'm not going to do any problems because I did that activity. I went through the whole activity and solved the problems there. So I'm hoping that's enough for you to go off of. If you're still not understanding stuff from 5.4, hopefully that'll help you. For 5.5, this one is, this is kind of a tougher one. If A and B are denumerable, remember denumerable means that there exists f from the natural numbers to A, so that's A being denumerable, such that f is bijective. Means we have a bijective function from the natural numbers to A, and we also have a bijective function from the natural numbers to B. Since it goes both ways, we could say there's bijection between A and B, but I'd rather focus on this idea of sequences. So if you watch the video for 5.5, I talk a lot about this idea that this bijective function from a natural number to A, this is the same thing as being able to list out the elements of A without repeating anything and exhaustively. So every element of A appears in the sequence somewhere, and no element of A is repeated. That's the same thing as a bijective function from the natural numbers. So A and B being denumerable, since A denumerable, we can list out the elements of A. A equals, let's say, A1, A2, A3. So every element of A looks like A sub n for some n. It's exhaustive and there's no repeats. And same thing for B. We can list out the elements of B, B1, B2, up through, B sub n and continuing on. Now the thing I will point out here is that this is very similar setup to in section 5.5, theorem 5.84, that if A and B are disjoint denumerable sets, then A union B is denumerable. This is very similar. You start by listing out the elements of A because you know it's enumerable, and then you list out the elements of B. And with union, we just alternated, right? We came up with a sequence of A union B by going, okay, A1, B1, A2, B2, A3, B3, and so on, and we'd be able to list out A union B. Here, we're not so lucky because this is a cross product, so our elements look different, so we can't just do that. However, this cross product, there's an idea that goes with this. Think about the rational numbers, how the rational numbers were proved to be denumerable. Remember, we made this array where the rows were the numerator, or rows were the denominator and columns were the numerator. And we were able to list out all of the elements of the positive rationals in that array. And then we took the diagonals, right? We kept writing the next diagonal, and we were able to list out the elements one-dimensionally in that way. So we're going to use the same idea as the rationals. Because positive rationals, when we did that, that's really, these are in a one-to-one correspondence with natural numbers cross the natural numbers, or at least a surjective correspondence. I have to think about that, but that's the analogy here. With Q, it was really natural numbers cross the natural numbers. Here we just have A cross B, but I can list them out just like I can list out the natural numbers. And so I'll do that. A1, A2, A3, A4, and so on. And then B1, B2, B3, and so on. And I'll just make my, oh my gosh. All right, back up, don't do that. I will make a table here. So a two-dimensional listing. And what we learned from proving the rationals were denumerable, or at least the positive rationals, is that if I can list out the elements two-dimensionally like this, then I can write the diagonals and list it out one-dimensionally. So how am I doing this chart? Well, this in here would be A1, B1. That'll be my first element of A cross B. And then here I'll have, let's say, A2, B1, and A3, B1. It's very similar to how we did the rationals, only here I'm thinking of ordered pairs rather than fractions. This would be A1, B2, and so on. A2, B2. I don't want to list out every single thing here, but maybe I'll do one more down here, A1, B3. And so in this chart, then I will have, since the list for A is exhaustive and the list for B is exhaustive, I'll have every single ordered pair will appear somewhere in this chart. And since no elements are repeated in either list, no elements will be repeated here. But we know even if there were some, we would just say, okay, just don't include it if it's repeated, like we did with the rationals. And then our rule for coming up with the sequence, and this is really all you have to tell me for this problem, for a proof for this thing, is just tell me the rule. So go by the diagonals. And in fact, since we already know about how we did the rationals, if you just draw these arrows, this is really telling me that you have the right idea. And I would accept that. And so we could start listing out the elements of A cross B. So A cross B then, right, we'll do the first diagonal, A1, B1, and then we'll go down to the next diagonal and take that one, A1, B2, A2, B1, and then we'll move on to the next one, A1, B3, A2, B2, A3, B1, and so on. And we can hit every single element. And so that proves that A cross B then is denumerable because we can list its elements out. And so honestly, a solution like that, you might write a few more words. It's kind of harder for me to say a lot with my digital drawing pad. But just, yeah, saying in words, hey, this is the rule. Look, I can list out the elements of A cross B, hence it's denumerable, and maybe a few sentences that say something like, we'll hit everything because A and B were listed out exhaustively, and so on. Okay, that's all I wanted to show you. I'm done with this video. Thanks for listening. I hope it was helpful for you. Took maybe longer than I thought it would, but yep, hopefully it's worth it. All right, see you later.